One of the things that's nice about an integral is that you can use them to get interesting information about three-dimensional objects. For example, you can use them to calculate the gravitational attraction of a three-dimensional object or the object's mass. And I want to show you something that's a little easier than that. So on the path to getting to those things which are a little complicated, you can first calculate the volume of a three-dimensional object. And specifically, I want to calculate the volume of a three-dimensional object that's been created by taking some function. So in this example, I'm going to use a straight line. Take this function and rotate it around an axis. So if I take the line y equals r over h times x and rotate it around the axis, this gives me a three-dimensional cone that has a height of h and then a radius of r. So I want to be able to calculate the volume of this thing using an integral. To do that, I'm going to do something like Riemann sums, where you use rectangles to fill up the area under a curve, and you added up the areas of the rectangles to get an approximation to the area under the curve. Then you got better and better approximations by using more and more rectangles. And then you got the exact area under the curve by taking the limit of that sequence of approximations as the number of rectangles goes to infinity, or equivalently, you can take the limit as the width of the rectangle shrinks down to 0. So here, to get an approximation for this volume that I can make better and better by using more and more of these simple three-dimensional objects, I'm going to use little cylinders or discs, and they're going to look something like this. So I'm going to cut up this cone into pieces, little discs like this. If I was just using 2 of these discs to get a very rough approximation, the first one would go from here to here, it would be real small, and the second one would go from here to here, it would be too fat. But as I use more discs or cylinders to approximate this thing, it would look something like this. So I'm imagining that I have these little cylinders, these discs, whose volumes I can calculate easily, and then I add them up. The width of each of these I'm going to call delta x, and that width is going to get smaller and smaller as I use more and more discs in my approximation. All right, so to get to the integral that gets the exact volume, I first write down the approximation of adding up the volumes of each piece. So the volume of this little cylinder is take the area of the base times the width or the height of the cylinder. So the area of this base is just going to be pi r squared, where the radius r of an individual disk is found by grabbing an x value somewhere in that disk and looking at what the y value is along this line for that specific x value. So this radius is really the y value. So I get the area of the base times the height. The height is delta x. And then if I take the limit of this as delta x shrinks down to 0, so I'm getting better and better approximations, it will give me the exact volume. And in the limit, in symbols, remember this delta x turns into a dx. And this sum turns into a stretched out s. We're integrating with respect to x, so we're going to be going from 0 to h. And then the y value is this radius. So I'm going to have pi times, and I need to write that y value in terms of x because that's the variable that I'm integrating with respect to. So I just plug in this r over h times x and square that. And then if you walk through this, if you simplify this, take the antiderivative, plug in the bounds, you will get out the equation for the volume of a cone whose height is h and whose radius is r. This method is called the disk method of calculating a volume. It's really nice. Sometimes when you rotate your object around, you want to like have a hollowed out 3D thing. So you'd have to cut out an inner circle. And then instead of having these disks, you have something like washers. So if you modify this to cut out a hole, it's sometimes called the washer method, but it's still the same method really. And then there's one other method that you sometimes need to use when your object is particularly challenging to find the volume of with the disk method. That's called the shell method, and I'm not going to teach it here, but I just wanted to give you a heads up that there is one other way to do this in special situations. So you still need to get some practice getting your hands dirty, actually making some calculations with some specific examples here, but hopefully this gives you a pretty good idea of where this thing is coming from, where the formula is coming from, and how you can adapt it in the future.